So kinematic equations for a constant acceleration. The 5 equations, you already know one of them. That was from the lab experiment or demonstration. And the other 4. So if we start with an acceleration time curve. Acceleration time meters per second squared. So meters per second squared, time on the horizontal. And the reason was so we can line up our graphs with the velocity and displacement curve. Let's say we start off with a constant acceleration. Say 10. The 10, it's meters per second squared. And it's a constant value with time, so it's not changing. If we want to go from that acceleration to a velocity curve, we're looking at the velocity is the area under an acceleration versus time curve. So the area under this acceleration time curve is going to give us a velocity, and that's what Newton discovered. Basically, after your algebra, the 2 new processes or functions you have area and slope. So by taking the area under an acceleration curve, in nature, you're going to get a velocity curve. So our velocity and the units, so 2 things labeled on the vertical, meters per second for the units, quantity is velocity, our quantity time, and unit second on the horizontal. And let's say we have 0, 0, maybe 1 second, 2 seconds, 3 seconds. If we drop a line down, 1, 2, 3. Keep going down. All right, the area, if we were to take a very small rectangle, 0 width and 10 meters per second squared height, since multiply by 0, that will give us a 0 value. So origin. If we were to take a larger rectangle, let's say the base is 1 second times a height of 10 meters per second squared. So 10 meters per second squared times 1 second. Seconds will cancel, leaving meters per second. And that's what we have, velocity in meters per second. So 10 times 1 gives us a value of 10. If we were to go to a larger rectangle, we would have twice the area, and that would look like this rectangle here. The bottom is 2 seconds, and the vertical would be 10 meters per second squared. Multiplying to get the area, we would have 10 meters per second squared. Seconds to the second power. 2 seconds, the seconds cancel, giving us 20 meters per second. So now we have velocity units, 20 meters. If we're to go to a larger rectangle, that would give us 30. And we get a nice straight line. And remember, in nature, everything's a nice straight curve, linear, second order, like a parabola. Could be that exponent, that poetic one, 1 over x. Could be e to the minus t. Or it could be a sine wave. Those are the common curves in nature. All right. So we're expecting one more graph. Time again on the bottom in seconds. And our next one is displacement in meters. Origin. And what Newton discovered. Displacement is the area under a velocity versus time curve. So area under a velocity time curve. All right, let's say we take a very small triangle. Base of 0, height will be 0 also, and that would give us 0, 0. If we're to go down to 1 second, at 1 second, we'll have a triangle So let's find the area there. Base is 1 second, height is 10 meters per second. Multiplying, you're going to get 10, half of that, 1/2 base times height. That gives us 5. So 5 meters. If we're to look at 2, so let's get another triangle. How about we make a triangle here? That'll give us, if one triangle is 5, then 5, 10, 15, 20. That should give us 20. That should give us a point at 20. And just to verify it, we have a triangle, 2 seconds. So including units, 2 seconds. The height is 20 meters per second. The area is going to be equal to 1/2. The base, 2 seconds. The height, 20 meters per second. The 2's cancel, leaving us 20 meters. And units also, seconds cancel, 20 meters. There's our 20. And if we're to go to 3 seconds, 1/2 base times height, that will give us 45. All right, and the curve here, it's definitely not linear. Linear is not going to work. It does look like a second order. And you can kind of imagine, what about if it starts over here? Nice parabola. And again, we're ignoring everything on the left side, but we do have this parabola on the right hand side. Okay, so just in nature, what Newton discovered. All right, what about if we start from the bottom? So, let's say we have our 3 curves. That's going to give us an acceleration. Meters per second squared. Seconds, let's say it's 10. We have another curve. Velocity in meters per second. Time in seconds. And that was at 10, 20, 30. So we had a nice linear graph for velocity, a linear constant for acceleration, and over here we had 5, 20, and 45, 0, 0. Displacement in meters, time in seconds. In this case, what Newton discovered was that if you start with this displacement, we could take the slope. So our velocity is the slope of the displacement versus time curve. Alright, and does that make sense to us? Again, remember, this is going to be a parabola, so it's curving at the very bottom. So think of a nice slope here. So from our pen, the slope at the origin is a horizontal line, which is 0. So at 0, we get a slope of 0. If we're to go to 1 second, we have some type of positive slope. Okay, I'm not really sure what the value is. Let's say hypothetically it's 10. So there's a slope, let's say it's 10. If we were to go from 1 second to 2 seconds, looking at the slope of this pen, it seems reasonable that's about double the slope. So if we had 10 at 1 second, we have 20 at 2 seconds. And then at 3 seconds, does it seem reasonable that it would be 10, 20, 30, 3 times the slope. And there's our slope. Now, if we start with the velocity curve, then our acceleration is the slope of the velocity versus time curve. All right, and does that make sense? The slope everywhere is the same value. And you can use a triangle here, you can come up with slope. Let's say the slope over here, if we create a small triangle, 10 over 1, that gives us 10. A larger one, 20 over 2, 30 over 3. And even at the origin, the slope is the same. So that gives us a nice constant value of 10. Okay, so now for the equation. Kinematic equations. Let's start at the top. We have acceleration is equal to a constant. Okay. To go from this acceleration curve to the velocity curve, we need to take the area. So our velocity is really equal to the integral of acceleration with respect to time. So that looks like acceleration, but a is a constant, so it's just going to be a times t, plus some constant. All right, and let's say that this constant is initial velocity. So v is equal to at plus initial velocity. Rearranging it, v is equal to v initial plus acceleration times time. And that is our second equation. So that gives us the second equation. The first one was from our demonstration class. Students, you did the data, you record the data, the measurements, we came up with a table, graphing it, came with a nice linear expression, looks something like this middle graph, which gave us distance, rate, time, or your first equation. Okay, no acceleration there. All right, what about this one? To go from this middle curve to the bottom one, so velocity to displacement, again, area. Okay, so the concept is we want to take the area. So area over here, slope to go this way. Going from displacement to velocity, slope, velocity to acceleration, slope, acceleration to velocity, area under the curve, velocity to displacement, area under the curve. So let's do that. Our displacement is equal to the integral of velocity with respect to time, but our velocity is this value. So v initial plus acceleration times time with respect to time. Take the integral of that. So constant initial velocity times time plus 1/2 at squared plus a constant. And let's say this constant is initial displacement. So x is equal to, and pull this around to the beginning, x initial plus v initial times time plus 1/2 at squared. And that is your third equation. Okay. A little bit of math. We could work on the last equation. So you have the relationship, the graphical relationship between these. So that's equation 2, 3. Equation number 4 is just going to be a rearrangement. So actually, let's look at that fourth one. That's pretty fast to get. So let's take the second equation and the third equation. So from your second equation, our initial velocity equals final velocity minus acceleration times time. So let's solve for that initial value. We want to get rid of this initial velocity in the fourth equation. That's the one from the Princeton Review study guide. And combine that. So equation 3. And substituting this initial velocity. Which will give us our initial velocity, our initial displacement. Over here we're going to have plus Vt minus At squared. So we have a negative At squared, but we also have a plus 1/2 At squared. When we combine the two, you have a negative 1 plus 1/2, that's going to give you a negative half. So x initial plus V final. So now it's V final instead of V initial. That's just going to save you maybe 30 seconds to a minute on a multiple choice question possibly. So it's minus 1/2 At squared. And that is our fourth equation. So you have your distance, rate, time. You have your second equation that came from the calculus, what Newton discovered. You have your third equation that's coming directly from the calculus off of a constant acceleration. So these only work with constant acceleration. If you have a change in acceleration, go straight to calculus. So if your acceleration has a function of time, you have to use calculus only. But if it's not, if it's a constant value, you can always stick with algebra, use your kinematic equations. That gives you 4 equations. All right, if we start off with that second equation. Second equation, velocity is initial velocity plus acceleration times time. And again, that fifth equation, there's no time involved. So physically, it doesn't seem to have much of a meaning, but a lot of algebra has been solved so that you can work directly with it. And it's very nice if you have a question that does not ask for the time. Okay, so looking at this one, we could solve for time. And our time would be final minus initial velocity over acceleration. The next thing we need to do is look at velocity, average velocity. So the bar above, that means average velocity. 2 different ways of looking at average velocity. One method, let's say that we have 2 values. In physics, we're only looking at the initial and final, so we could just take 2 values only. Think about an analogy of 2 test scores. You have 2 math scores, one's 100%, one's 90%. Your average would be 95. So you can add the 2, divide by 2. So we could say our initial and our final, initial plus final. So initial plus final divided by 2. So that's your initial velocity plus your final velocity divided by 2. That'd be like 100% and 90%. Add them, divide by 2, gives you the 95% average. Okay. Another way of looking at your average velocity is the definition. So change in displacement over change in time. Okay, but our displacement is final minus initial, x minus x naught, and our time, we're going to use a stopwatch, so our initial time is always 0. So it'll be final time minus 0. Alright, so let's combine these two. Combining these two, so the average velocities, making those two equal. So that's our average, equals our definition, x minus x naught over t. Alright, and then the time. So we need to get rid of that time. So let's get rid of that part now. And that's from equation number 2. So we want to remove the time. So just algebra now, put in this value. We need to put that velocity over the acceleration. So the acceleration is on the top. All right, and when we multiply these two velocity terms, velocity plus initial velocity. The acceleration is now up on the top, so 2 times acceleration times our change in displacement. Alright, so we have some terms here. It looks like the middle terms are going to cancel, but we'll have a final velocity minus initial velocity squared.